previous lecture, what we have seen is that the quantum hypotheses that is an oscillator can take energies 0, h nu, 2 h nu and so on, explains the black body spectral density. So, this is only the oscillator. So, what we had assumed that there is a cavity and these oscillators take only quantized values, but at the same time we are treating the radiation as if it is continuous. There seems to be an inconsistency, and that is where Einstein came in, and he said maybe radiation should also be treated as discontinuous, containing particles of energy h nu, and he went on to show this. I want to do it for you because this is a beautiful piece of scientific investigation. So, what Einstein says is that for a system where Wien's formula for radiation is valid, and that is a regime where nu over T is large. When this is valid, the radiation behaves like a collection of particles, each with energy h nu, and that gives the concept of photon. And we want to see how he did that. We use a little bit of thermodynamics, right. So, thermodynamics says that 1 over T is equal to ds by du at constant volume. Now, what Einstein considers is that S is also made up of a spectral S nu d nu. There is a spectral distribution of the entropy, just like U is given by u nu d nu. And without proof, I am now going to claim that 1 over T is also equal to d S nu over d u nu at constant volume. So, even the partial, whatever the spectral density of the entropy is and of the internal energy is, their partial derivative gives you 1 over T. So, what we have is 1 over T equals d S nu over d u nu. Now, from Wien's formula, we have u nu is equal to some alpha e raised to minus beta nu over k T, and there is a nu cubed. So, u nu over alpha nu cubed is equal to e raised to minus beta nu over k T. Take log of both sides and you get log of u nu over alpha nu cubed is equal to minus beta nu over k T, or 1 over T is equal to k over beta nu with a minus log of u nu over alpha nu cubed. And therefore, I have 1 over T, which is minus k over beta nu log of u over alpha nu cubed equals ds nu over d u nu. We integrate this and we get s nu, small s nu is equal to integral minus k over beta nu log nu minus log of alpha nu cubed d of u, which is minus k over beta nu u log u minus log of u log of alpha nu cubed. Let me simplify this. So, let me see what we got. We have got s nu equals minus k over beta nu, k over beta nu. Inside I get u log of u minus u log of alpha nu cubed, which I can write as minus k over beta nu. U I can take out, log of u over alpha nu cubed minus 1. This is S nu. This is the entropy density. So, now I consider in this cavity a small interval of d nu. So, the entropy of the entire cavity is going to be volume times S nu d nu, which I can write as minus k u d nu times V over beta nu log of u over alpha nu cubed minus 1. Now, notice that u d nu times V is the energy contained between u and d nu. So, S is equal to minus k times the energy over beta nu log of, I can write this as u d nu times V again. So, energy over alpha volume nu cubed d nu minus 1. This is the entropy of radiation. So, I can write this in entropy of radiation between frequency nu and nu plus d nu, right, in volume V. Now, consider change the volume from V1 to V2, keeping E unchanged, keeping the energy of the system unchanged. Then you are going to get, so S1 is going to be minus K E over beta nu log of E over V alpha nu cube d nu minus 1. This is V1. S2 is going to be minus K E over beta nu log of E is remaining unchanged, V2 alpha nu cubed d nu minus 1 is going to be K E over beta nu log of E over V2 minus log of E over V2 alpha nu cube d nu plus log of E over V1 alpha nu cube d nu. So, this gives S2 minus S1 is equal to K E over beta nu log of V2 over V1. So, this is the change in the entropy of radiation when E is kept constant and volume is changed from V 1 to V 2, and this is also under the condition that nu over T is large. Okay, so, T is small. Now, let us compare this with an ideal gas change of entropy. If I take an ideal gas, fill one half or one portion of a container which is isolated from surroundings, right, of V 1, and this whole volume is V 2, and puncture this wall. When I puncture this wall, what happens is this entire container gets filled, and there is a change in entropy. And this change in entropy can be calculated very easily. What we do is push this gas back to volume V 1, keeping the temperature the same. If the temperature is kept the same, if T is kept unchanged, the internal energy of gas also remains unchanged. And I leave it as an exercise for you to show that in this case, if you calculate the entropy change, you get S 2 minus S 1 to be equal to N R log of V 2 minus V 1, V 2 over V 1, where N is the number of moles and R is gas constant. So, what we have learned is that in case of radiation, the change in entropy S 2 minus S 1 came out to be K E over beta nu log of V 2 over V 1. We know the value of beta is h. So, this is K E over h nu log of V 2 over V 1, which I can write as K is nothing but R over N is the Avogadro number, E over h nu log of V 2 over V 1, and in gases S 2 minus S 1 comes out to be N R log of V 2 over V 1. So, this means we can consider the radiation as having number of moles equals 1 over n E over h nu, right, number of moles equals this much, and behaving like an ideal gas. So, this also implies then immediately that E over h nu is equal to the number of radiation gas particles. So, that 1 over n is the Avogadro number, E over h nu becomes number of moles. So, this analogy between entropy change of the radiation when it is allowed to change its volume without changing the energy and ideal gas gives you an idea that it can be treated like a collection of molecules, but that is just showing it theoretically. To check the validity, one needs experiments. Okay. So, for that Einstein proposed checking it through photoelectric effect. So, let me just give you again that S2 minus S1 came out to be Ke over h nu log of V2 over V1, and if we take energy of each radiation molecule to be h nu, then K E over h nu comes out to be Nr, just like ideal gas, and that is what gives Einstein the idea that I can think of this as a collection of particles with each having energy h nu, and n becomes n e by h k, e by h nu becomes Nr. Okay, and then through photoelectric effect it is checked and everything comes out to be correct. I am not going to do photoelectric effect here because you have studied it many times in your 12th grade and so on. Okay, so, this is what gave the idea of radiation also having this particle nature of h nu, and experimental evidence was photoelectric effect. He also applied it to some other effects called the when the radiation goes out, radiation hits an atom and goes out, its frequency change is such that the wavelength increases, its frequency goes down. So, it has given part of its energy to the atom. What we will do next is again apply Einstein's ideas to study the low temperature behavior of solids, to see that the ideas of quantization of an oscillator can also be applied to mechanical oscillators.